On April 22, 2021, a catastrophic engine failure on a 460-foot-long passenger and car ferry near Bainbridge Island, which is near Washington, started a fire that caused more than $3.8 million in damages. On March 14, 2022, the National Transportation Safety Board concluded its investigation into the incident and tied the fire aboard the Wenatchee to an improperly tightened fastener. A single nut. The fire occurred during a sea trial in Puget Sound after the fastener failure led to components from the engine being ejected and causing a fire in the engine room. Luckily, none of the 13 crew members were injured, and their swift action prevented it from being worse. The issue dates back to November 2020, when the Wenatchee, operated by Washington State Ferries, was taken out of service for maintenance. During maintenance, 2 of the 4 main diesel engines were overhauled by factory-trained technicians. In February 2021, the crew conducted engine tests following the overhauls. Alarms went off in the number 3 main engine, and crew members found pieces of a cigarette lighter in the lube oil system. The maintenance technicians came back, drained the oil, and searched the lube oil system for 2 days. They recovered about 70% of the cigarette lighter's plastic and metal components and told Washington State Ferries that it was fine to run the engine. However, none of the engines were run again until the vessel headed for a sea trial. In April, during the post-maintenance sea trial, the connecting rod assembly in the number 3 main engine failed and ejected components that breached the crankcase and ignited hot pressurized gases. The crew contained the fire by stopping all fuel supply and ventilation to the engine room and isolating the space. One crew member witnessed, quote, "fire, smoke, and debris flying everywhere." Engineers examined the lube oil system to see if the cigarette lighter could have caused the engine failure. While they found parts of the lighter throughout the system, they found nothing that would suggest the lighter parts started the fire. The NTSB found that the probable cause of the mechanical failure was the connecting rod assembly that came loose due to insufficient tightening or torquing of a lower basket bolt during the previous engine overhaul. The NTSB stressed that maintenance technicians should use a calibrated torque wrench in compliance with the manufacturer's recommendations and verify that all required torque requirements had been completed. This is not the first time that improperly torqued fasteners have caused problems. A fire aboard the Carnival Liberty cruise ship in 2015, a fire on the Nanita bulk carrier in 2016, and an engine failure on the Red Dawn offshore supply vessel in 2017 were all traced back to bad fastening, according to the NTSB. The Wenatchee was built in 1998 and can carry up to 202 vehicles and some 1,800 passengers, so it could have been much worse. All because of a, quote, engine assembly error, or nut that just hadn't been torqued right. The operator cooperated with the investigation, provided recommendations to prevent future incidents, and is designing and installing a video camera system with fire and smoke sensors for the Wenatchee and other vessels in its class. I'm David Manti. Tighten those nuts.
Hello and welcome to today's webinar. I hope you found that clip regarding improper fastening aboard that ferry very enlightening to see that a part that may only be a few dollars in cost, if not properly torqued correctly, can cause millions of dollars in damages. And so I'm glad that you're joining us today as we look at 3 ways that we can help to control torque through the use of a cam over style torque wrench. And so my name is, wrong way there. My name is David Cash. I'm a member of the marketing team here. So thanks very much for joining us. And again, let's go ahead and jump right into today's presentation. So as we look at the different manufacturing risks, we just highlighted one that was a human error. And this is one of the largest reasons that we do have issues with torque and torquing correctly is the human element. So if there are ways that we can help to eliminate the possibility of a human error, this can really help us with controlling that application with the manufacturing process. Next, we're going to be looking at over tightening. Now, with many styles of wrenches, over tightening can be an issue. So if we're looking at, say, a click wrench, for example, this wrench is a very operator dependent style of wrench. And we're going to talk a little bit more about that as we go through. But typically when we're talking about torque and the possibility of improperly torquing, the over tightening is certainly an issue. Under tightening as well can also be an issue, because any type of vibration that may happen, that fastener may release and then again cause failure. But if it is over tightened, that can also lead to fastener breakage as well. As we move a fastener that has been over torqued, we're actually stretching that fastener past its yield point. And we're moving into the plastic region of that. And so we have a little clip here. This kind of demonstrates what we're talking about when we're looking at fasteners that may have a tendency to break due to over tightening. So every fastener that we're dealing with has a tensile strength to it. So we can stretch it to a certain point. But once we do stretch it to a certain point, it can then go ahead and relax and come back to its original shape if we remove that tension to it. However, once we get to the yield point, that fastener will begin to deform. And once we see that deformation, it's basically at risk of breaking at any moment due to any type of shock, again, or any type of motion jarring that is going to cause that fastener to break because it has moved past its yield point with that particular fastener. And so if we look at this graphically, you can see that the first peak there is going to be our yield point, and everything below that is going to be the elastic region of the fastener. So again, if we move that fastener to a specific torque value, as long as it stays within the elastic region, we are providing sufficient clamp load to that. Once we move higher than that, we're moving into the what would be the plastic region, and again, at any point we can see failure as we add additional torque to that, or if the fastener itself breaks because of other external forces. So if we can help to control that, again, we can make sure that the fastener is in the correct region. So what are some of the other risks that are associated with the parts that fail? Obviously, high scrap rates. If you do have components that need to be reworked, again, that's causing time, also money, and additional work that may not necessarily be needed. Finally, we're looking at the lack of an error-proofing process. Again, if we can help to eliminate any type of error that can be generated either by the tool or by the person or the operator that's using that tool, then again, we have the ability to control that application and the output that we are getting from our tools. And then if we have the proper tool for that application, that can help to mitigate any type of manufacturing risk as well. So with the proper torque control within the assembly process, if we have the correct tool with the correct process, if we're applying the right amount of torque, not under tightening or over tightening, this will give us, again, an enhanced process reliability and efficiency. We can ensure that there's conformity throughout the assembly process, and we can help to eliminate and reduce scrap rates with that. So that is the ideal situation that we would be looking for with our torque control process. Now, is your quality process at risk? Well, let's go ahead and take a look at the 3 ways that we can help to improve the process by using a cam over style tool to prevent any type of over torque event. And so first is if we can help to eliminate the operator influence. As I mentioned, with certain types of tools, there are a lot of areas where the operator can introduce error or improper tightening to that application. So if we have, again, the proper tool that we can help to give the operator that can help to reduce that, we can implement an error proofing style of tool that can certainly help, or we use a preset style tool to enhance the reliability that does not give the operator the chance to change a preset or change an adjustable style tool to make sure that they're moving that tool to the correct torque. So a preset style tool can help to eliminate that as well. Next, as we just mentioned, the preset style of tool can be used here. You can certainly tell what a preset tool looks like compared to an adjustable tool. A preset tool does not have a scale on it. It may be printed or stamped with the range of that tool. Because the tool is adjustable to a certain preset value, that is done internally with the either adjustment tools to do that, and then that tool is verified on a torque analyzer, as compared to an adjustable style tool that may have a scale on it. Obviously, you would try to adjust that tool, but we want to make sure that we're giving the operator the best chance of doing the operation correctly by using a preset style of tool. And then thirdly is going to be the actual torque wrench mechanism that is being used. And so there are a number of different styles of torque wrenches. And so all torque wrenches do apply torque. However, not all torque wrenches apply torque the same way. So that's going to lead us into the different styles of wrenches. First is going to be the click wrench. And by far, this is the most widely used wrench in the world as it relates to torque and assembly. And there are a couple of reasons for that. First, they are very inexpensive to be used, very inexpensive to purchase, and they're very easy to use. The issue with the click wrench is that it really only has about 3 degrees once that wrench clicks before it basically becomes a non-torque tool at that point. So if you pull on a click wrench and the wrench clicks, but you keep pulling, you're adding additional torque to the assembly process. What about if you double click or triple click that wrench? Again, you are adding additional torque to the assembly process, and you can add up to double, triple the amount of torque that you would see with that. And so if, depending on who is pulling the wrench, again, a very operator-dependent style of tool that will produce different results based off of who is pulling that, maybe their attitude or how they are feeling. If the wrench is not clicked or pulled with a slow, intentional type of movement, over torque will be seen with that particular tool. So that is the click wrench. Another style of torque wrench is going to be a breakover style of tool. In this case, we have a signal when the torque is achieved, very much like a click wrench. When that wrench clicks, that is signaling to stop pulling on that wrench. A breakover style tool has a much greater degree of signal. So we can have up to 90 degrees of break in the head before we would be adding additional torque. It makes it very difficult to be able to do that. And we'll show you what that looks like during the demonstration process. But a breakover wrench does give you the ability to help eliminate the operator influence, provide the correct torque that would be needed within the assembly. So that is the breakover style of tool. next is going to be the cam over wrench. And so as we're highlighting the cam over style of wrench today, in essence, this wrench will never give you the ability to over torque a fastener. So if you have a really critical type of application where you need to make sure that that is not over torqued, a cam over style tool is going to be the best option for you. So once that wrench reaches the certain torque value, it will simply slip, and then the follower goes into the next cam. And again, you can try to apply torque to it again, but we're never going to go up higher than the torque value for that particular wrench. Now, the cam over wrench is a preset style of tool. So you do have that ability to adjust the tool within a certain range depending on which item or which range of that tool is being used. Again, the operator does not have the ability to adjust a cam over style tool without actually going inside of the tool to do that. But these tools then are verified and double checked on a torque analyzer to make sure that the torque output is correct. So again, the cam over wrench helps to eliminate any type of operator influence. It is a preset style of tool, and it's going to give you the proper torque delivery during the application process. And so what are going to be the accuracies that we might see with different wrenches? As I mentioned, the click wrench, it is a signaling type of wrench. It is going to give you that point at which the torque is achieved. But again, if the operator does not stop applying torque or pulling on that, that is adding additional torque to that. And the accuracy can be at risk for a click style of wrench. The breakover style wrench, again, also a signaling type of wrench, but it does give the operator a much greater chance of not over torquing. And there is a real clear signal at once or when that wrench actually reaches torque with the break that you would see while it is being used. And finally, the cam over wrench. This is going to be the best option to help remove any type of operator influence in that. It doesn't matter who is pulling on that wrench. It is always going to provide the correct torque to that. So the other big advantage of the cam over wrench is that it is also a non-length dependent wrench, meaning you can hold that tool anywhere up and down the handle of that tool, and it's going to produce the same amount of torque output at the drive or the end of the tool. That's because the fulcrum point is actually at the end of the tool, as opposed to a click wrench, which the fulcrum point is inside of the wrench. And so any type of movement, if the tool is not held in the correct spot on the handle, we're changing the actual torque output to that. And you can see that with the torque or distance times force. That is going to give you your torque output. And again, it's because the pivot point or the fulcrum point is inside of the wrench. We'll also show you what that looks like here as we come up through our demo section. There's also one other style of wrench that we didn't really touch on, but that's going to be a digital torque wrench. The digital wrench acts very much like a click style wrench. It is going to give you a signal once torque is achieved, and you can stop pulling on that wrench once you get to that signal. Now, there are different ways that they can alert the operator. You can have a much larger window that is going to provide either a beeping, a visual scale, or a possible vibration in the handle to alert the operator. But again, these digital style wrenches are a static style of tool. They are always going to be positive unless you stop pulling on it once you reach your torque value. Again, opposed or in conjunction with a cam over style tool, no matter how many times you try to pull it. Once that wrench cam's over, you've hit your torque, and you can't add any additional torque to that. So that's going to lead us to our poll question for today. And in that, as we go ahead and launch that, what style of wrench do you currently use in your process? Is it a click wrench? Is a breakover wrench, a cam over wrench, a digital, or is it going to be a mix of those particular items? So let's go ahead and let you give you an opportunity to answer those questions, and we'll go ahead and then move on from there. All right, that is, we've got quite a bit of responses here. The highest wrench that's being used is the click wrench, and followed by the actual leader of the poll, which is a mix of different style of wrenches for that. So thanks very much for participating in that. And let's go ahead and then jump into our demo portion of today, and this will help us to get a closer look at how these tools operate and what we might see. And so right here I've got two samples of click wrenches, and just to show you basically how the click wrench works and its components, I basically took this wrench apart, and you can see here we have our torque spring, which is going to be generating our torque values. We have our follower, and then we have our jump block or pivot block, and this is the item that actually will provide us with our torque values. So as that wrench begins to be used with the follower inside here, and then the pivot block, it sits inside this little channel on the follower. And then once this spring begins to compress, this will actually cause this block to pivot inside this follower. And so if we zoom in here a little bit, let's see here. You can see the pivot block sits right inside the follower, and as the spring is compressed on here, that block will cause the bottom head of the drive section to actually come in contact with the inside of the torque wrench. And this is what gives us our click sound and either audible feel, our sensory feel that that wrench has clicked. And so, again, as I mentioned, with the wrench itself, it's a non-length dependent wrench, meaning that if I don't hold the tool where it's meant to be held, or if I move up, we're going to be changing the torque, because our actual fulcrum point is at the end here where that block is going to pivot. So if we take a look at what this looks like on a torque analyzer, let me go ahead and move this out of the way. We'll bring our analyzer in here. And so if I have my wrench set, or let's go ahead and set our mode here to peak. So this is going to capture the highest peak torque. With this wrench, it's currently set at about 10 inch-pounds or so. So if I pull on this wrench, you can see, well, I got 22, 14, 18. So we're getting much higher results than we would see at the setting of 10. Let's go in and we'll change the mode to first peak mode. And this is actually going to capture the moment at which the wrench clicks, and then it's also going to show us any over torque that we might see. So our wrench is clicking here, and you can see we're getting a much higher torque value than where our wrench is actually clicking. So we're not actually making it in here. But if I do pull on the wrench and we get our click, you can see that we're here and we're not getting any additional over torque to that. Now you may see some erratic readings here on the analyzer. It's because I don't have this necessarily secured to the table here, but nevertheless, this can show you the inconsistencies that you can have with a click wrench. And so if the operator double clicks, you can see we're adding 22 inch-pounds. Again, very much operator dependent when you're using a click style of wrench. Now the next wrench that we're talking about, we're going to be the breakover style wrench. So this is our TB wrench. This one will go ahead, and once torque is achieved, the wrench can break over to more than 90 degrees. But at the point at which the wrench begins to break is where we've hit our torque value. So we have a much better visual on when we want to actually stop pulling on the wrench. We also have this style in a larger style of wrench, so our 2BX wrench. These are available with interchangeable type of heads with that. And again, once this wrench begins to break, we've hit our specific torque value. So if we want to test this, we can do that again in our peak mode. Go to our actual setting. And I think this one's set at around 20 inch-pounds or so. So we'll go ahead and use that as our target. If I go ahead and drop this into the drive, as I apply torque, once we get the wrench breaking, we'll go ahead and we get our torque value, and we can go ahead and stop pulling. Again, we're not adding additional torque to the actual application. So we're getting a much better signal and a much better accuracy than we would see with the click style wrench. Again, these tools have multiple styles of heads. You can use a box end like we have here. If you want to use an Allen key on the end of those, you can do that as well. Or if you have a ratcheting drive, in this case, this would also give us that same type of breakover. Set this one to, I think it's 9 inch-pounds. And again, as we're using this and we apply load, once we get to where that wrench breaks, you can see that we're not adding additional torque to that. Again, you have a much better control over the torque delivery than you would with a click style wrench. And then finally, we have our cam over style tool. This will go ahead and again, it will slip in the drive. We've got several versions of this style of tool depending on the range that you might be looking for. But again, they are adjusted internally. You're probably not going to be able to see inside there, but we would put a specific tool inside here to either turn up or turn down the torque depending on the range that the tool is giving. So let's see, I think this one is set in the 30 inch-pound range. So let's go ahead and set our target to 30 on the analyzer here. And make sure we're in the peak mode. That's going to give us the highest peak that we might see. with that. And so, yeah, so we're in 34. If I pull again, let's go ahead and do that. 33. And if I keep going and try to keep going, we're not adding additional values to that as we would be with a click style of tool. And so the cam over style wrench is by far going to give us the best accuracy that we might see for very torque critical applications where you may need to make sure that the output that you need does not exceed the actual torque that you need. Now, is this going to be used for every application? No. Some of the applications may not require that much concern. So a click wrench may be, again, a viable and good option depending on the application. Just want to make sure that the operators understand what they are doing and how they can influence that torque value if you do want to use a click style wrench. And so with that, that's going to lead us to our questions and answer section for today. So let's see. Chris, do we have any questions?
Good morning. Good morning, Dave. First question we have is, does it matter on where you grip a wrench? Does it impact the torque output on different wrenches?
Yeah, yes, it does. And that's kind of what I was mentioning about the cam over style wrench being a non-length dependent, meaning we can hold that anywhere up and down the handle on either the breakover style or the click wrench. We do need to make sure that we're holding it where the tool is designed to be held, or it's going to change the torque output. And that's because, again, our fulcrum point on the cam over tool is at the end of the wrench, and on the click wrench, it's inside that wrench.
All right, Dave. Next question was regarding accuracy. What's the difference between accuracy and repeatability with the tool?
So again, if we look at, say, an archery target or a bullseye, accuracy is going to be how close we come to the actual center of that bullseye. And then repeatability is going to be how closely grouped are the results in conjunction with each other. So we can have a tool that is extremely repeatable, but it's not very accurate because it's not at the target. We can also have a tool that's accurate, but not very repeatable because of the same, just in reverse. We may have, on average, a good reading because we're getting to the target in some cases, and then we're outside of that target on one side, maybe outside of the target on the other. So on average, it appears accurate, but it's not very repeatable. So that is the main difference between the accuracy and repeatability. Obviously, we would like the tool to be accurate and repeatable within a certain percentage of the target that we're trying to look for. Chris, are you still with us?
I'm here, Dave. Sorry, I lost my sound.
Okay.
The last question we had is for the breakover wrenches. Why is the torque length dependent? And do you have like a diagram that we can show engineers about the grab point?
We certainly can do that. Yeah, the TB wrench has an indicator on the handle where you're supposed to be pulling that. And that gives the operator a really good reference point at where they need to be for that, and also with the TBX as well.
For the cam over versus click wrench, can you use an extension, or will the extension impact the torque value? Is another question we just got.
Yeah, so if we do add a spanner or a crow's foot to the end of either of those wrenches, we would need to check on a torque analyzer what that output is going to be. We can calculate that mathematically, but now this changes the the cam over wrench, where again, now we're changing the fulcrum point where the output is. So we can use an extension with either wrenches, but we would need to compensate for the additional distance to the force that would be generated. So there would be the need to do that. And again, then we would need to make sure that we have that tested, but we can also add the equation mathematically to figure out what our torque output is going to be as well.
Another question I has, what's the range of the cam over wrenches, Dave, in general?
So we can go low in the range. You could go up to 90 or so foot-pounds with those wrenches. And I believe we're down in the about 1 Newton meter all the way up to 100 Newton meters, 125 Newton meters with that. So those are there's several different tools within certain ranges from that all the way up.
All right, dude. That's all the questions we have for today.
All right. Again, we thank you very much for joining us today. We look forward to next month's webinar as well. So go ahead and look for those suggestions coming to you. Again, have a great weekend, and thanks very much.